Hi, welcome to Probabilistic Programming 1, the Introduction to Bayesian Machine Learning. Before we get started, a general note on the probabilistic programming sessions. In these videos, I will take you through the most important parts. I will not go through everything, but I do encourage you to read the rest of the lecture notes at your own pace. They contain a lot of information, and I'm just condensing them to the gist of it. Let's get started. We're going to start with a beer tasting experiment. So in the summer of 2017, students of the University of Amsterdam participated in a beer tasting experiment. Each participant was given 2 cups and were told that the cups contained Hefeweißbier, one with alcohol and one without. So they taste each beer and guess which of the 2 contained alcohol. So we're going to do a statistical analysis of this tasting experiment. We want to know to what degree participants are able to discriminate between the alcoholic and non-alcoholic beers. We're going to use the Bayesian approach, which consists of 3 core steps. Specifying a model, absorbing the data through inference. So we're going to observe data and then estimate parameters. And we're going to evaluate the model. Right. So the model specification usually consists of 2 parts, a likelihood function and a prior distribution. A likelihood function is a function of parameters given observed data. This will become clear in a moment with an example. So suppose we have this event variable x, and this is going to indicate whether the participant's choice was correct, x is 1, or incorrect, x is 0. We're going to say that this x is a random variable and that it follows a Bernoulli distribution. Bert has talked about the Bernoulli distribution extensively, so I won't go into too much detail. It has a rate parameter theta, which is a number between 0 and 1, which governs the probability of the 2 events. So the higher the number gets, the closer it gets to 1, the more probable it is that you're going to observe the outcome x is 1. And the lower the value for theta, the more probable you're going to get the outcome x is 0. So the formula for the Bernoulli distribution, we usually write p of capital X, which is the event variable, is equal to lower x, which is going to be 0 or 1. Given theta is a Bernoulli of small x given theta, whose functional form is theta to the power small x times 1 minus theta to the power 1 minus x. So you'll see that for the event x is 1, this probability distribution consists purely of this number theta, and for the outcome x is 0, this probability distribution purely consists of this number 1 minus theta. Now, if you have a data set, if you have multiple independent observations, then you can get the probability of all of those observations by taking the product of each of the individual probabilities. So P of the entire data set given theta is the product over the individual xi given theta. So suppose we have 2 participants that have correctly guessed the beverage, so 1, 1, and a third one that incorrectly guessed it, so that's a 0. And say that we are looking at the probability theta equals 0.8. Then the likelihood function tells us that the likelihood of this particular value for theta is 0.128. If we're looking at a different value for theta, so 0.4, then we're going to see a lower value in the likelihood function. And if we're looking at theta is 0.6, then we might find a higher value for the likelihood. And so in this likelihood function, we vary the theta, and given the data remains fixed, that tells us something about how well the parameter fits the observed data. And usually we say that in short, the likelihood function tells us how likely each parameter value is. The Second part of model specification is a prior distribution. A prior distribution governs what the probability is of the unknown variable, so that's in this case theta, the rate parameter, before you have observed data. So prior means before and posterior means after. So in this case we're going to use a beta distribution as the prior. So we say that P of theta is the beta distribution of theta given two parameters alpha and small beta. This gigantic term first, that's a normalizing term. We're going to ignore that for the most part. We're just going to look at this part, theta to the power alpha minus 1 times 1 minus theta to the power beta minus 1. Now let's have a look at what this function looks like. First, in Julia, you would have to use packages. It's the same as with Python. In Python, you import packages. You can even import submodules. In Julia, we do that in a similar fashion. We have the command using. In this case, we're using the software package PKG, which stands for package. We're going to activate a workspace which contains all of the packages necessary for the probabilistic programming course, and then we're going to instantiate that workspace. That means that we're bringing all of these packages into scope. We're automatically downloading them if they have not been downloaded yet. If I uncomment the clear output, it's going to give us a response saying that it activated the environment. Now we want to use two specific packages. One is called distributions, which is a library of parametric probability distributions, and the other one is called plots, which is for plotting. PyPlot means that we are using Matplotlib, or Python's plotting library, as the backend for this plotting library. Julia works really well with other programming languages, especially Python, and so that is actually a quite common command that you're doing here. Right, so let's have a look at the prior distribution P of theta, the beta. It is governed by, so currently it looks like this weird line going down. If I change these parameters, then it's going to change shape as well. So that's why these two parameters, alpha and beta, are called shape parameters. And we feed that to a beta function, a beta method, which is part of the distributions package. We're calling that P of theta. Then I'm defining a range of values for the variable theta. We said before that it takes a value between 0 and 1. So the starting point is 0.0 and then the stopping point is 1.0. We increment this range with 0.01. Now I'm going to plot the probability of each value of theta under the beta distribution. And you might see that there is this. So PDF is a function from the distributions library. We can apply that to a distribution object. This dot is a broadcasting operation, which means that instead of computing the PDF of the entire range of thetas, we are computing the PDF for each value in the range of theta. And so that's what you see here, this plotting line. The remaining arguments in this plot function, so line width, color, label, x label, you might recognize these from Python. They're virtually the same as in Python. Another thing you might have noticed is that we are using Greek letters. So in Julia, you can specify Greek letters just like you do in LaTeX. You open a /, you type alpha, and you press tab. That completes it into the Greek letter of choice. You can actually use this in your plotting as well. So you don't have to specify a particular command like LaTeX. You can just directly complete that into the Greek letter, and then it will plot that Greek letter. Right, so the keen observer might have noticed something else, namely that the probability here in this part of the graph is larger than 1. So the general rule for probability distributions is that they should be positive everywhere and they should integrate to 1. Your intuition that a probability should always be less than 1 is based on discrete distributions. In discrete distributions, the integral becomes a sum, which means that the sum of probabilities should be 1, which means that every probability is smaller than 1. In a continuous distribution, it should just integrate to 1, and you can define intervals in this range where probability is actually larger than 1, as long as it in total integrates to 1. So here I've shown you a few versions of the beta distributions for various combinations of shape parameters. We're going to walk through this piece of code a bit more because I'll show you how looping works in Julia. Before we get to that, let me show you a very important difference between Julia and Python/MATLAB. So a square bracket, 2 numbers with a space in between them, so no comma, without a comma, produces a row vector, 1 by 2. And if I use a comma there, then this produces a 2 by 1 column vector. If I produce a semicolon, it also produces a 2 by 1 column vector. Note that this doesn't work. This does work in MATLAB, but doesn't work in Julia. You need to remove these commas, and then you'll get a 2 by 2 array. So in this case, we have 2 column vectors, alpha with 2 values and beta with 2 values. We're going to loop over these entries. So I'm defining a variable in this range of values, alpha, another variable in this range of value, betas, and then I'm going to plot them. Now you might have expected a hold on command here, but that's not the case. You'll notice that there's this exclamation mark here. So in general in Julia, whenever you see an exclamation mark following some function, that means that you are actually changing a thing, so an array or some other data structure, or in this case a graph, a plotting structure. You're changing that in place. So for arrays, that means that you're not making a copy of the array and then changing something. No, you're going into where that array is located in memory and then changing values there. So you're also not recovering. You cannot recover the original value. So in this case, we start an initial plot. That's the first line. That's this beta 1,1, the blue line here. And then for every iteration of this double for loop, we are modifying the graph, modifying the figure with by adding another plot on top of it. And so we'll get all combinations of these 2 factors. So there's 2,1, 2,2, 5,1, and 5,2. So that's the rest of this list. So as you might see, the beta distribution is quite flexible. We can get straight lines out of this. So the beta 1,1 is a special case that's known as the Uninformative Prior. It's called uninformative because every value of theta has the same probability. So the prior distribution contains no information. It doesn't favor one value of theta over the others. You can get an increasing straight line, you can get an arch, you can get a skewed distribution with a bump here, and you get something that increases exponentially. So let me first summarize the prior distribution. It is a probability distribution of some unknown variable, in this case the rate parameter theta, that reflects our beliefs about good values for that parameter before we observe data. So in this example, it reflects how well we think people can discriminate alcoholic from non-alcoholic beer before we've observed data in the experiment. So if you think that people are unable to discriminate that, you might think that the value theta's 0.5 should have a high, should be the maximum value in this probability distribution. And if you think people are always going to be able to discriminate between them, then you think that 1 should be the largest value in this prior distribution. Right, so I want you to try for yourself. or there are blocks here, but I want you to try things for yourself. I want you to pick values for these shape parameters alpha and beta that reflect how often you think the participants will get it right. So what is your belief about this parameter before we observe data? So try it for yourself, and then I'll see you in the next video.